This is your science recap for April 28th and 29th, and we are mostly continuing on with our STAR review. We're going to keep working on that STAR review packet. Today we focus on day 2. Today we'll review all of our physics that we learned at the beginning of the year. F equals ma, Newton's laws of motion, S equals d over t, speed, velocity, acceleration, and motion graphs. Remember that when you're completing that packet, to use the STAR review page linked in Canvas here. So your virtual science journal is there, and again, each button is linked to a different Prezi, a review presentation. Day 2, today, you're going to need to use this physics button again. We also use that day 1. So you're going to make sure that you go through all of that. Additionally, beneath that, you'll see the physics unit overview. So those will probably be useful to look at. The learning targets, essential questions, vocabulary Quizlets for all of those terms and those things that we learned at the beginning of the year. As far as independent work, make sure to complete all of the day 2 portion today, so all the way up to question number 45. And then we also are going to ask you, look back over your chemistry unit test. If you need to do a second attempt, reach out to your teacher, go over any questions that you don't understand, and take care of that. For the STAR review packet, let's go over the information from day 2. So we first reviewed force equals mass times acceleration, and you'll always be given that formula. That's part of your formula chart. You'll get it when you take the STAR test. You get it on any quiz or any test. And so first we practiced, how do we solve for things besides F? And so we set up this triangle, and if you remember that if things are next to each other, that means we have to put them next to each other in the triangle, and we multiply them together. If something is on top of something, that means that it's a fraction. We divide. And we use this thumb method to figure out what we solve for. So you put your thumb over what you're trying to solve for. So if I wanted to know what F is equal to, I'm left over with m times a, force equals mass times acceleration. If I'm trying to find the mass of an object, I put my thumb over m, and I'm left with F over a, force divided by mass. F over a, force divided by acceleration. Acceleration is force divided by mass, or F over m. And so if you can just set that up, that's going to help you solve for any one of these 3 variables. The first practice problem, we're given the mass and the acceleration and asked to calculate the force. So we simply multiply those 2 numbers together. 2,000 times an acceleration of 3 is 6,000 newtons. In the 24, we're asked to solve for acceleration. So acceleration is equal to force divided by mass. So I'm going to do 45 divided by 0.5. My acceleration then is 90 meters per second squared. Remember with acceleration, whether we're given it in this previous problem or here when it's the thing we're solving for, the units themselves are squared. We don't have to do any squaring. It's just part of the units, but you shouldn't be squaring any numbers. If we're trying to figure out the force acting on a car and we're given this different data table, what we really have to look at is how can we rearrange and use the data to find the variable here. So I know that it's the same cart being used in all of these different tests. And I know force equals mass times acceleration. So step 1 is I'm just going to find what's the mass of the cart. I know force and I know acceleration, and so I can do F over a, 1 divided by 0.2 to find the mass. And I can plug all of these in, and I'm going to get the same mass, it's 5. So at the end, that same cart is being used. I know the mass of the car is 5. I know the acceleration is 2.6. To solve for force, I simply multiply those to get 13 newtons. We next spent a lot of time reviewing Newton's laws of motion. And it's important to remember that all of his laws of motion really apply simultaneously anytime you have something moving. Inertia is just that things keep doing what they're doing unless there's an unbalanced force, so it'll stay at rest or it'll be in motion. The law of force and acceleration is us solving F equals ma. And action-reaction. For every action force, there is an equal and opposite reaction force. We can look at seat belts. The anti-inertia belts keep you from flying forward in your car if you hit the brakes suddenly. When you hit the brakes suddenly, your body's accelerating because you have a mass, and the force of the brakes is applied to that mass. Action-reaction. Your body pushes forward on the seatbelt pushes back on you. Sometimes it even leaves a bruise if it's a strong enough push if you're in a bad enough accident, which is way better than hitting the windshield. Hitting a baseball, we could apply the same ideas. The ball doesn't move unless there's an unbalanced force applied to it. If you apply a greater force to the ball, that ball, its mass, will accelerate more. Action-reaction. The bat hits the ball also hits the bat. If you've ever looked at a baseball bat, you see dings in it. That's because the ball's hitting it. Roller coasters. When you fly around a corner and your body kind of whips around, it's because your body was trying to keep going straight, but then the cart pulled you along, so your inertia wanted you to keep going in the same direction. When you're going downhill, you speed up. That force of gravity is causing your mass to accelerate. And just like a seatbelt, that safety bar pushes back on you as you push forward on it. Rocket launches. Once rockets are up in space, they actually don't need to turn their ignition on or turn their make some exhaust unless they're trying to change direction, speed up or slow down. Once a rocket's in space, they just keep going. They have inertia. There's no unbalanced force to change it. You need a huge force because rockets have an incredible amount of mass to accelerate. They also need to escape that unbalanced force of gravity. And rockets launch based on third law. The exhaust, when you burn the rocket fuel, the exhaust, the hot gases push down. The equal and opposite is the hot gases push up on the rocket. So we can think about Newton's third laws, or all three laws, as we look through the different questions. Glue makes it stable to hold a heavy object or load. If the load exerts a strong downward force, so remember, third law, for every action there's an equal and opposite reaction. The glue, so here are our force pairs, our load and our glue. The glue must exert a upward force that is equal to the downward force. So equal but opposite, up versus down. When a car comes to a sudden stop at a red light, a grocery bag lying on the cart slides forward, spilling the contents of the floorboard of the car. Why does it continue to move forward? There wasn't an outside force to change it. The bag had inertia, which caused it to keep going in the same direction and speed. When we look at rockets taking off of a launch pad, this is really, again, action-reaction. This is third law. So the hot gas are pushing, the rocket pushes down with the hot gases, equal and opposite. The gases push up equally against that rocket. A student sitting in a wheelchair at rest throws a basketball forward. The student in the wheelchair have a greater mass than the basketball. So yes, there's equal and opposite forces. The student applies a force to the ball applies a force to the student, but because the student in the wheelchair have much more mass, it accelerates less. It has more inertia, it's harder to accelerate it. So it's going to move backwards, but it's not going to go faster than the basketball. They're going to go slower than the basketball because the student has more mass and it's harder to overcome that inertia. Number 31 is another inertia question. We did this and looked at some demonstrations earlier in the year in class. The coin is at rest. A student can apply a force by flicking the card, but the student did apply a force to the coin, so the coin stays there. But then we know it doesn't hover. There's this unbalanced force of gravity that's going to pull that coin down into the cup. We also looked at reviewing how to solve speed, distance, and time. And our formula says average speed equals total distance over total time. Usually we just abbreviate it, S equals D over T, but pay attention if you're ever asked for average, that you do look for the total and the total. So if S equals D over T, I know that D has to be in top in my triangle. So that leaves S and T. So again, my thumb method, S is equal to D divided by T. D, distance, these are next to each other, they multiply. Distance is equal to speed times time. Time, D over S, that's a fraction, that's division. I can then use that to solve various problems. Average speed of a cheetah that travels 112 meters in 4 seconds. Well, so speed is distance over time. My distance is 112. My time is 4, so I plug into my calculator 112 divided by 4, 28 meters per second. The next problem, if we look at a cannon and we're told the speed of the cannon and the distance the travel went, we want to know how long. That's a time. So time is distance over speed. The distance the cannonball is going to go, or the human cannonball, is 200 meters. The speed was 350 meters per second. So if I plug in 200 divided by 350, I'm going to round approximately 0.57 seconds. The next problems are asking me to look to the graph to the right here. Remember that the steeper the line, the faster that object is moving. It's covering a greater distance in a shorter time period. So the animal that has the fastest speed is the animal with the steepest line, which is the Canadian goose. How far does a hummingbird travel in 60 minutes? The hummingbird is this dashed line in the middle. In 60 minutes, the hummingbird has gone right between 30 and 40, 35 kilometers. What is the speed of the monarch butterfly in kilometers per minute? So again, speed is equal to distance over time. Because the butterfly, which is the dotted line at the bottom, is going at a constant speed, it doesn't matter what points I pick on my graph to plug those in to solve. So I'm just going to go right to the end. So 30, 45, 60, this must be 75. So the time is 75. The distance is 25. If I plug in my distance divided by my speed, I get approximately 0.3 kilometers per minute, a third of a kilometer every minute. Number 38, we're asked to find average speed of a ball in this graph. And if I look to the graph, which is a distance time graph, the ball is changing its speed because there's different slopes. It's going slow, it gets very steep and is pretty fast, and then kind of goes at a slightly slower rate. Average speed, again, if I look to my formula chart, total distance over total time. So I'm just going to go to the very end. At the very end, the total distance was 10 meters. The total time it took to go 10 meters was 50 seconds. So if I plug into my calculator 10 divided by 50, the average speed is 0.2 meters per second. Speed, velocity, and acceleration are also things we reviewed this year. Speed is simply how fast you are going. We could calculate it by doing speed divided by distance divided by time. Velocity, remember, is the same thing. It just includes the direction. North, south, up, down, left, right. Acceleration is a change in your velocity, and there's 3 ways you can accelerate. Speeding up is the most common one, slowing down, or changing direction. If we're looking for the best description of velocity, we're again looking for a speed with a direction. So for speed, I need to have a distance per unit time. So in letter C, 30 meters per second is a speed, and east is my direction. Number 43, we're given some different vehicles, and they're all traveling at the same speed, but the pickup truck is changing its velocity, which is here. Why? So velocity, remember, is speed plus direction. It's not changing its speed. We're told they're all traveling at the same speed, but it's on a corner. It's changing its direction. So that is why it is accelerating. That is why it's changing its velocity. The last couple questions today ask you to review some motion graphs. And the first thing to remember is read the title, read the labels. We have motion of a toy car. We have time on the bottom, always, but pay attention to your why. Sometimes you'll have distance, sometimes you'll have speed or velocity. So on a distance time graph, this first part here means that train is going at a constant speed. That curve down is slowing down. And that flat part, their distance isn't changing over time. Time is passing, you can't stop time, but the distance doesn't change. That means they're not moving. They are stationary or have stopped. So the best description of that is letter C. Moving along at a constant speed, slowing down, stopping. The next graph is showing velocity over time. So now our y-axis is different than distance. At what point is the object traveling at a constant speed? So if we think through our graph and think about what's happening to our y value, between A and B, the velocity is increasing. It's speeding up. B and C, it has a velocity. Its velocity is 20 meters per second, but it's not changing. So that's a constant speed. I'm going to abbreviate that. Between C and D, again, my velocity is increasing. It's speeding up. D and E, it doesn't change. It has a velocity, a constant velocity of about 40-ish. Here, I'm slowing down. F and G, I also have a constant speed. My velocity is about 20. G and H, my velocity is increasing. I'm speeding up again. So as I look through all of my choices, even though I have 3 here, only one of these 3 constant speeds is going to be on my graph. It's not A and B. B and C, yes, it is a constant speed there. Make sure that you reach out to your teacher if you have any questions. That is it for your day 2 wrap up.